So we've seen that the Cobb-Douglas matching function is a very popular choice when we need to assume functional form for the matching function. However, it has one limitation, is that there's no guarantee that the Cobb-Douglas matching function is less than the minimum of its two arguments. And that poses a problem when you work with a discrete time model. And so when it's like that, what you do is you're going to assume instead, it's quite common, a constant elasticity of substitution matching function. Because the CES matching function has a nice property that it's always less than its two arguments. So here's what I mean exactly. So we saw the Cobb-Douglas matching function. So Cobb-Douglas matching function, if you have a number of sellers S, number of buyers B, omega, which is a matching efficacy, S to the power of eta, where eta is a matching elasticity, times B, number of buyers, 1 minus eta. Now, here you can see that if S or B are large enough, then what you can have is that the matching function is strictly greater than the mean of S and B. So if you have, you fix B, and at some point, if S becomes large enough, of course, you'll have more matches than the minimum of S and B. And similarly, if you fix S as B gets big enough, you have no guarantee that the number of matches is less than the minimum of S and B, which is a requirement. If you work with a discrete time model, the matching function gives you the number of trades that are realized in one period. And of course, you don't want the number of trades realized in that period to be more than the number of buyers or the number of sellers, because of course, you can't have more trades than the number of sellers or the number of buyers. So we always want that the number of trades is less than the minimum of the number of sellers and buyers. But with a Cobb-Douglas matching function, that's not necessarily the case. So if you work with a discrete time model, then you have to impose that your Cobb-Douglas, usually the way to do it formally is to impose that the Cobb-Douglas matching function is, the Cobb-Douglas expression, except if it becomes larger than the mean of S and B, and in that case, it becomes the mean of S and B. But so it's complicated, it means that you can't just use the Cobb-Douglas function, you need to impose an extra constraint. And so that's inconvenient. You don't really want to have to do that. And so instead, when you work with a discrete time model and you want to make sure that the matching function is less than the mean of S and B, then you're going to use a CES matching function, a matching function with constant elasticity of substitution. So what is the CES matching function? It takes this expression, this form. So the matching function, when the number of sellers is S, number of buyers is B, it's going to be S minus gamma plus B minus gamma to the power of minus 1 over gamma, where gamma is a parameter that has to be strictly greater than 0. So this is our CES matching function. So let's check that all the properties of the generic matching function are satisfied here with our CES function. Okay, so what do we want to check? So first, of course, we want to check that the matching function, when there are no buyers, no sellers, or no buyers, is equal to 0. And here that's going to be verified, right? Because let's say if S is equal to 0, S minus gamma, since gamma is positive, that's going to be infinite. And then something infinite to the power of minus 1 over gamma, that's going to be 0. Because the key thing is here is since we assume that gamma, the exponent is positive, minus gamma is a negative number, minus 1 over gamma is a negative number, and so that ensures that when either the number of seller or the number of buyer is 0, the matching function is equal to 0. So that's going to work. Something else that we have to check is that the derivative of the matching function with respect to the number of sellers is positive, the derivative of the matching function with respect to the number of buyers is positive. So the matching function is increasing in number of sellers, increasing in number of buyers. And here you can verify that too. We know if the number of sellers goes up, number of sellers to the power of minus gamma, that's going to go down. And then once we put that to the power of minus 1 over gamma, which is another negative number, that's going to go up. So you compound S with a decreasing function and then yet another decreasing function that gives you something that's increasing. Same argument for what happens when you increase B. If B goes up, B to the power of minus gamma, that goes down. And then once you put that to the power of minus 1 over gamma, that's going to go up again. So clearly the function is increasing in the number of sellers and is increasing in the number of buyers, which is a good thing. Oh, we also need to check, of course, that our function has constant returns to scales, and that's pretty easy to check. We need to check the CRS properties. So for this, we can just compute the function where we multiply both inputs by some scalar lambda. And that's going to be lambda S minus gamma plus lambda B minus gamma to the power of minus 1 over gamma. All right, and so here what we can see is that we can factor out the lambda minus gamma. And then once we take that exponent out and bring it to the power of minus 1 over gamma, that's going to be just lambda, because minus gamma times minus 1 over gamma, that's just 1. So that's just lambda plus B minus gamma minus 1 over gamma. And that's just lambda M of S and B. So we check that indeed we have constant return to scale here. And the last thing that we can check with our CS matching function, of course, which was the motivation for that function in the first place, is that at any point in time, the matching function is less than the minimum of the two arguments. So we want to check that the matching function for a given number of sellers and buyers is strictly less than the mean of the number of sellers and buyers, so that the number of trades is never more than the short side of the market. And we said with Cobb-Douglas there was an issue that the number of trades could be more than the short side of the market, which would require us to impose that extra constraint that we want to take the mean of Cobb-Douglas and S and B. Here it's not going to be the case. The CS matching function is always less than the minimum of the two arguments. So to check that the matching function is less than the minimum of the two arguments, we can first note that S minus gamma plus B minus gamma is strictly greater than S minus gamma. That's of course because B to the power of minus gamma is positive. Now, what I'm allowed to do is take both sides of this inequality to the power of minus 1 over gamma. But because minus 1 over gamma is a function that's strictly decreasing, then what we need to do is, because we have a strictly decreasing function and we take both sides of the equation through this strictly decreasing function, I need to change the sign of my inequality. So I get this. Now, what we see on the left-hand side is just the matching function at S and B. And what we see on the right-hand side is S minus gamma to the power of minus 1 over gamma, and that's just S. So here what we've established is that the matching function is less than the number of sellers. But of course, I can do exactly the same with the number of buyers. And what I can then show is that the matching function at S and B is strictly less than the number of buyers, following exactly the same argument. And therefore, because the matching function is less than these two things, it's in particular the matching function at S and B is going to be less than the minimum of S and B. And so we verify, therefore, that that matching function naturally satisfies this condition. So you never need to add any restriction once you use the CES matching function, unlike what we had with Cobb-Douglas. In addition, so one good thing with the CES matching function, we see that it has one parameter, the gamma. And so you can, Cobb-Douglas has two parameters, so it gives you even more flexibility, but nevertheless, here you have one parameter that you can calibrate based on real-world data to try to match what you see in the real world. And so you can at least choose the value of that gamma parameter to match real-world data. One last thing that I want to point out is that the matching elasticity in the case of the CES matching function is not going to be constant, unlike what we had in the Cobb-Douglas matching function. So you remember, and that's a very important elasticity in matching models. So the matching elasticity is just the elasticity by definition, the elasticity of the matching function with respect to the number of sellers. So that's the definition of our matching elasticity, the elasticity of the matching function with respect to the number of sellers. It's something that's measured in empirical work. And so there are a lot of estimates of the matching elasticity. It's something that plays a big role also when we think about efficiency. It's one of the key statistics that shows up in Hosius condition. So matching elasticity is something that's important in matching models. And in the case of the Cobb-Douglas function, the matching elasticity is constant. It's one of the parameters of the Cobb-Douglas function. But with the CES matching function, it's actually not constant. It's going to vary with the tightness of the market. So it's good to be aware of that property. So let's compute the matching elasticity in the case of the CES matching function. So it's eta, it's d log m, d log s. So it's d log of s minus gamma plus b minus gamma to the power of minus 1 over gamma. All right, so now we know that the elasticity of a function with an exponent is just the exponent times the elasticity of the function inside. So that's going to be minus 1 over gamma d log s minus gamma plus b minus gamma with respect to s. But now we know that the elasticity of the sum of two functions is just the weighted average of the elasticities of each function, where the weight is just the relative size of that function in the sum. So here, b minus gamma, we know that it doesn't respond to s, because here we have partial derivative. So we know that this is just going to be the elasticity of s minus gamma times the weight, so s minus gamma over s minus gamma plus b minus gamma, the weight of s minus gamma in the sum. And that's just another properties of our elasticities. And this we can simplify further, so it's minus 1 over gamma, s minus gamma plus b minus gamma. And then the elasticity of s minus gamma with respect to s, well, that's just minus gamma. Okay, so here we have the -1 over gamma minus gamma that simplified to just give us 1. So here we find that eta, the matching elasticity that we were computing, which is just the elasticity of M with respect to S. So that's just going to be equal to S minus gamma over S minus gamma plus B minus gamma. And this we can simplify greatly. If we divide numerator and denominator by S minus gamma, we get that the elasticity eta is just 1 over 1 plus B over S minus gamma. But then you remember that B over S, that's just the market tightness, the ratio of buyers over sellers. That's just our market tightness. And so now what we can see is actually the matching elasticity with the CS matching function is itself a function of the market tightness. So in general, we know that the trading probabilities, selling probability, buying probability are functions of the tightness, but with the CS matching function, the elasticity, the matching elasticity is also a function of the tightness. So in fact, what we have here is that eta is a function of theta, the market tightness, and it's 1 over 1 plus theta to the power of minus gamma. And so here in particular, what we can see is that this matching elasticity, the matching elasticity is going to be an increasing function of tightness. And so when tightness is 0, so theta is 0, theta minus gamma is going to be infinite, so the matching elasticity is going to be 0. And then when theta is infinite, theta minus gamma is going to be equal to 0, and then the matching elasticity is just going to be 1. So these are useful properties and things that may be handy when you work with a CS matching function. So the elasticity when the tightness is 0, that's just going to be 0. The matching elasticity when the tightness is infinite, so as we said, that's just going to be 1. And in general, the matching elasticity is increasing in the tightness, as we can see from its expression. So we have an elasticity that between 0 and 1, and that increases with tightness, going all the way from 0 to 1. So this is a property that arises here, that you do not have a constant matching elasticity.